So hello, everyone. Thanks for joining us for the third class of CPH 290. I think the last two lectures we had academic speakers who talked about applied machine learning for healthcare from an academic perspective. Today we have a special guest from one of the most exciting companies in the health AI space. So today it's a pleasure to have Zachary Ziegler, who is the co-founder and CTO of Open Evidence, which is the leading AI-powered medical information platform. Open Evidence is designed from the ground up for medical professionals. It organizes the world's medical knowledge to make it more useful, open, accessible, and understandable. It was launched out of the Mayo Clinic platform Accelerate. And Open Evidence now is used in over 7,000 care centers across the US and over 150 countries around the world. And before founding Open Evidence, Ziegler was a PhD student at Harvard University, where he worked with Professor Sacha Roche and was awarded the NSF Graduate Research Fellowship. He also completed his undergrad at Cornell University, where he received a Barry Goldwater Scholarship. Thanks so much, Zach, for joining us today, and I'll hand it over to you.
Okay, thanks so much. It's really nice to be here. I'm someone that I've always found myself in these types of interdisciplinary programs or interdisciplinary situations one way or another. My background getting here has been pretty nonlinear. I started out in undergrad in physics, and also at the time I was kind of teaching myself how to program and doing different kind of side projects and all sorts of different stuff on the side, and eventually transitioned into machine learning and natural language processing and computer science. And so I've always kind of found myself on the edges of different disciplines and at the intersection of different disciplines. And so, I think CPH, hearing about this, it's a really fantastic program. And I think there's a ton of value in combining different areas and bringing together people with different ideas and different backgrounds, and different contexts. And there's a lot of really important progress that can be made at those points. So it's great to be here. And in a lot of ways, Open Evidence is exactly that kind of interdisciplinary thing. It's a combination of, on the one hand, modern AI and large language models, and on the other hand, the application of healthcare. So I think this is a really nice fit here. There's obviously an enormous amount of discourse and conversation and communication around AI, and no shortage of opinions. So I'm really glad to be able to be here and fully set the record straight and make sure that we never have to have this conversation again, and we have the final say on the matter. So just to kind of level set for people who haven't explored Open Evidence or tried it out, I think just to give a little bit of context, this is Open Evidence. It exists just on the internet at openevidence.com. It's a kind of Copilot interface for physicians. And the idea is that physicians can enter any kind of basically medical question, and they'll get an answer after a bit of thinking, which is designed from the ground up for exactly what they need. It'll give them information that's purpose-built for physicians and clinicians, and then importantly is grounded in high-quality references and information, and makes the information actionable and trustable. So that's what we build. We put it out into the web, and we build a kind of community around it. But fundamentally, that's what we're talking about. That's kind of the core of Open Evidence. So in this talk, I'm gonna, there's really two parts that map onto the two kind of constituents of Open Evidence. The first is the technology, and I'll talk about large language models and really try to get at the heart of what really are large language models. What are these things? And can we use that understanding to gain insight into where we expect these models to perform well, and what is just obscene hype, essentially. And then in part two, I'll talk about the healthcare application specifically. Again, my background is technical. It's on the machine learning side. So what I'll talk about here, a little even more than the specifics of the medical aspect, is the business side and the kind of strategic decisions that go into making a healthcare startup. All right. So I challenged myself after deciding to come here to, in the last week, make a record of all of the ads and discussion and billboards and stuff that I saw, especially driving up and down between South Bay and San Francisco. And this is my presentation of what we got. A few of these are Reddit ads, then we see billboards. And there's just, I think probably this group is probably the last group in the entire world that I have to tell that there's just an insane amount of discourse and hype and publicity around AI. It's like every company in the world is trying to squish AI into their thing, no matter what it is. So Watson, IBM, of course, makes a lot of sense. On all these billboards, let's turn AI hype into hype-worthy results. Sounds good. AI trained to help, not hallucinate. Salesforce AI. My personal favorite that I saw and hadn't actually heard about before was the Intel AI PC. What does that mean? I don't know, but somehow, your computer is just AI, which sounds pretty good. And it's crazy. And then, of course, 2 days ago, probably the what I assume is the peak of this is the Nobel Prize in Physics being awarded to computer scientists for everything around here. So
I think chemistry as well.
And chemistry, yeah. Although I know less about the chemistry one. In some ways, this seems even more crazy. But yes, it's a weird time. And so what I wanted to do in the context of all of this is go back to what the world looked like 5-10 years ago when I was in graduate school, and dealing with these types of models in a less crazy world, and try to convey my understanding of kind of where these models came from, and hopefully get at the reality of these sort of things. So I see about three eras for language models, and I'm going to walk through them. So the first era of our tour here is what I call the toy system era. So this is now 5 or 10 years ago. Generative NLP, and specifically generative modeling, was at a state that was mostly theoretical and had a few applications. I'm someone that was always interested in applications on the ground. The one that always stands out for me is translation, in terms of where do people interact with generative modeling. Right, you go to Google Translate, type in whatever, and pretty magically you'd get a pretty good translation that was like decent a lot of the time. Another application here is captioning. I like this because it is an example of a different modality, but it's still about taking an image and then generating some text to be a caption for that image. And there's a whole range of these types of problems. I think these are the two easiest to understand. But the idea is that you're going to have some input and some output. The output's always going to be text. And your goal is to take a whole bunch of data, a whole bunch of input-output pairs, and use that to learn a distribution where you can generate, at test time, given some new input that you've never seen before, you can generate some output. So we're going to use translation for a bit because it's a pretty canonical example. The idea is you have a bunch of pairs. There's a bunch of training test pairs, and this is what we have as input. We're going to train our model with these types of pairs. And then at test time, again, you have this now new input. There's no output associated with it, and the goal is to perform translation. And the way that, so ultimately what we're talking about is learning a model. And so that we're going to parameterize that model with some distribution. This is a very just general notation. That means we're going to try to learn how to generate some output Y given some input X. And it turns out that just mathematically, a very convenient way to parameterize this type of distribution is to break it out into these telescoping terms of token by token likelihoods. And so what this says is that if you want to learn a distribution over something like a sequence of text, what you should do is at any moment have some function that takes whatever you're trying to condition on. So let's say some English sentence and some amount of whatever you've generated so far. And all you have to do is have some function that combines all that information together and generates the next token. So this is essentially comes from a statistical breakdown of what a probability distribution is. But this turned out to be an effective way to make models that would do important things like translation. What this would look like in practice is your model would take this English sentence and then it would just start generating. So it would generate the first word, and then it would condition on the first word and this English sentence and generate the next word. Then it would take the first two words and this English sentence and generate the third word, and so on and so forth. But really what, the important thing is that what these models are doing is just next word prediction. It's just saying what is the most likely next word given all the previous words. Now, what the function that is actually doing this computation is can be a lot of different things. And this is where you start to hear words that I'm sure everyone's here has heard, including like transformer and RNN and LSTM and these sort of things. From a probabilistic model perspective, what I think is not talked about much is that these things just don't matter at all. These are all equivalent, and they're really just implementation details in a lot of ways of what exactly is this function that does this computation. All right, so what does this look like in practice? So again, we have our training set, we have our pairs of inputs and outputs. We're Google, we're trying to make Google Translate really good. And we have the form of our model. So we've made this choice to have this telescoping, autoregressive, token by token type prediction. And essentially, at this point, when we have a model and we have data, we just use statistics. And statistics says that there's a pretty specific training algorithm. That's the process of training. And that process looks like a maximum likelihood estimation. So that details, I think, of that are not important. But what it means is there's a prescription to say, I want to maximize the likelihood of the true data inside my model. And that essentially you can think of as kind of a magic wand. But what it amounts to is training these parameters. So inside this function, this is a parameterized function. And the training process says, given my data, what should I set the values of all these parameters to be such that when I do this step-by-step type prediction, I'm doing the best job at generating the appropriate next token as it looks like in my training set. Okay, this is the height of math and details in this talk. So if we made it here, that's all we got. So far we've been talking about these conditional models and these very practical type problems like translation. It turns out that in the course of doing these things, statistics is hard, right? And actually doing this kind of optimization when you have a fixed amount of data is a challenging problem. What the kind of community started to do in terms of trying to solve this problem, which is commercial benefit, is say, okay, hold on, let's pause, let's try to simplify this problem as much as possible, and let's take the kind of simplest, most base case and see what we can learn about optimizing this problem in the base case. So we say, in particular, let's remove the conditioning. In a lot of ways, that's a detail that's not important to the process of generating language. It kind of reduces entropy, but whatever. It's just adding complexity, and let's get at the most simple form of this. And so when we do that, we get to a model that now is not concerned with doing this kind of conditional generation, which is, let's say, generate a French word or sentence conditioned on an English sentence, but it's just about how can we generate language? What does it mean to generate token by token? How can we learn the patterns of French or English or whatever kind of language? And so from my perspective, this is kind of the origin of the language model. When we say language model, what we mean is a model that's just unconditional, that just knows how to generate language. And that's really all a language model is when it comes down to it, is this toy system that was interesting for academic reasons to be able to eventually better understand these things that were actually in production and making money. What this looks like in practice is now we have training data. This training data is no longer pairs of inputs and outputs. It's just a bunch of sentences. And we're doing the same thing we're doing before. We're doing our same kind of training process. We're doing our same token by token prediction. But that's it. It's just, let's just throw some language at this thing and see how good it can learn a distribution that reflects that. And the reason to do this is that there's a lot of complexity inside these bubbles here. This is where, like I said, you can write papers that show that, oh, if we have a transformer architecture, it performs better than an RNN architecture. Or if you use this kind of regularization or this kind of loss function, those things perform better. And so there's a lot of value in being able to have a choice system like this that was very simple, that was very shared between everybody. And we could just optimize how do we do the best possible job at learning language. That's really why we started using these models in the first place. Really specifically, this is now the world that I was in during my graduate school. And there's lots of interesting things you can do. And it's just like fully academic. It's like that's all it is really. We can ask questions like, can we make VAEs? Can we have different interesting probabilistic models for this? Can we learn GANs, which were really popular a bunch of years ago? I was into normalizing flows as an example. VAEs were another example 5-10 years ago. But really, it was just this system that we were just like, let's play around with this and let's try to learn it, use this to learn as much as we can about like the kind of truth behind generating language. All right, so that's my view on the world of language models about 8 years ago, let's say, something like that. And coming back to the next era. The next era is what I call the pre-trained weights era. And the situation here is we're back in conditional world. So, we're back in the world that money defines. We want to be able to do translation. Facebook thinks if we do translation really well, we can get more users and expand our reach, for example, more broadly than the United States. Google is really heavily invested in translation. How do we do translation as well as possible? Well, the observation is we still have all of our input-output pairs. It's hard to get an enormous amount of input-output data that's really high quality. But we have an observation, which is that it's much easier to get an enormous amount of just language, unpaired data about what it means to be speaking, say, French in this case, or English in another case. As everyone knows, machine learning models are extremely data hungry. Data always substantially improves models a ton. And so the thinking is there any way that we can use all of this unconditional data, all of this language that we have to improve this conditional sense? And the answer essentially is yes, using language models as an intermediary. And this is the kind of intuition and thing that forms the second era here. This is, for whatever reason, characterized by Sesame Street. And this is the whole flavor of models that were Bert and Elmo and Ernie and Big Bird. And once the first person did it, then everyone else had to do it. And I don't know, we just went weird for a few years. And all of these are essentially different approaches of trying to solve the same problem of we have all of this unconditional data, all this language. How can we use language models that are trained on that data to allow us to do a better job at the problem that we're actually trying to solve? And the intuition for why we should expect language models to be a good proxy for for helping us use this data is that in the process of training a model like this, so this is again our friendly unconditional language model, in the process of learning this, inside each of these bubbles here, these are where all the weights are, and there's some neural network. And in order to actually predict the next word in a sentence, if you have a ton of data and you want to do this at a high fidelity, you actually have to know something pretty fundamental about English or French or whatever language you're learning. You have to actually know French, basically. And the kind of intuition is that knowledge of French is encoded somewhere in these weights, either in embeddings, in outputs of these weights, or in the weights themselves. And if we can train language models on this enormous amount of data, maybe in these different Elmo, Bert, Big Bird type approaches are all ways of kind of carrying over that information to do the downstream task that we're actually interested in doing. So this was the idea. We'd have, again, a ton of these unconditional sentences. We'd first train a large language model. Now I've been keeping track of these parameters, so we're talking about larger and larger models here. We'd first train a model here. Because we have a large data set, we can train a bigger model. We can train that over more data. And this knows French to a good degree. And then what we do, essentially in very slightly different ways is we initialize the weights of the model that we care about, the downstream conditional model with the unconditional model weights. Of course, at first, this is going to do a very bad job at translating, but it's going to know a lot about language. And then we just train. So these are now a deeper color of red, indicating that there's been a fine-tuning stage that happens. These weights have been updated. They haven't been updated a huge amount. They haven't forgotten French, but this knowledge about French that's been imbued from the outset has allowed the model to learn something about French and retain some of that information while also learning how to do the actual task of translation. And in practice, so these are the results from ELMO, which was the first real paper that showed this. This was an enormously exciting result actually for the NLP community at the time, because whereas so much of the work previously had been about how can we optimize the loss function? How can we optimize that? How can we optimize a regularization? How can we optimize architecture and all these things and get these relatively small improvements? For the first time, this like really blew out of the water the metrics and the performance on a large number of tasks. So these are a bunch of different tasks doing all sorts of different downstream things that we might want to do in natural language processing. And what this table is showing from the ELMO paper is these are the kind of baseline results without doing this pre-training, and these are the results with this pre-training. And in particular, when it comes to the relative improvement, these at the time were pretty enormous relative improvements, right? This is a 25% reduction in error rate. This is a 17% reduction in error rate. This is 21% reduction in error rate. So these were quite substantial, much more than we were seeing with these other types of things, and it spawned this cottage industry of Sesame Street knockouts, essentially, and really made a very large impact. All right, so that's the second era. That's the pre-trained weight era. The third era here is what I'm calling the standalone task completer era, and this is the transition, I would say, to where we are now, from something that was still kind of mostly academic to something now that is blown up and can be used by anybody. And I think there's really two things that have changed. Fundamentally, actually very little has changed. It's very similar, but there's two important things. So the first thing is the scale. So before we were talking about training over about 100 million parameters. Now, GPT-4 is at least a trillion parameters, which is just incomprehensibly huge, in my opinion. And the other thing is that in parallel with that, the size of the data set has grown to the extent where this is basically all of the internet is the way to think about it. And so that's thing one, is the scale is just enormous. And that, to OpenAI's credit, I think that's one thing that they pushed really, really hard on, was just like that there's value to purely just increasing scale. And so this is really just what with GPT-3, for example, when we were excited about GPT-3 a few years ago. This is just GPT-3. We take everything we've been doing exactly the same as before, and we just scale it up. But now the second thing is an equally kind of important change, a relatively small change, but it makes a big difference. And the sequencing is like, OpenAI puts out GPT-3 just on the internet as an API that can be used. And in the process of doing this, they collected a huge data set of things that people want to do. And so this is a data set that starts to get into the world that we're now much more familiar with, in terms of you're an expert poem writer, write some kind of poem, translate hello to German, extract the author's name, right? They were able to get now not just one task, but an incredibly diverse set of data about things that people want models like this to be able to do. And what they were able to do is take all those inputs and then just pay people to write really good outputs. So literally just construct paired training data. And what's interesting is that this scale of training data is not enormous, right? This is 30,000 pairs. That's not any really substantially bigger than, say, the translation data sets. But what's important about it is that it's really diverse, and it gives a wide sense of all the things that people want to do. On top of this, in this paper that I'm talking about at the bottom, so they do this supervised training step, which is the same thing we've been talking about before in terms of fine-tuning. They also add on to this kind of one step at the end of reinforcement learning. I'm not going to go super into that. It's kind of an optimization step on the end that definitely improves performance and is a way of leveraging more paired data, essentially. But it doesn't fundamentally change the conclusion, which is that what they did is scale up a model to a huge degree and then just collect a really good sense of how do humans want to be able to interface with this type of model. And the intuition here, I think, is pretty important and pretty striking. On the one hand, you have 10 trillion words and a 1 trillion parameter model. And on the right, you have 30,000 pairs of a little bit of information. So what's actually happening now when you do this training process? What's happening is that in this pre-training process, this is the process in which the model is actually learning everything. This is the process where the model is reading the entire internet and encoding in its weights everything that it knows about the world and its nuances. But it doesn't have the right interface at that point. It doesn't know, it's not aligned to speak the language of humans, basically. And in a lot of ways, I think what OpenAI did really well is that this fine-tuning process for them was much more a process of actually just like orienting the interface and telling the model, here's how you interact to human instructions more than anything else in a very general way. In these 30,000 pairs, it's not learning how to write a poem. It's not learning German in these pairs. It's doing that in this process. It's just about kind of learning the interface. That's what's happening here. But then the actual practical procedure is very similar, right? It's all the same thing. We initialize the weights with an unconditional model, and then we just do a little bit of fine tuning on top of that. And that's really it. As much as like 4.0 is literally, 01 these days is maybe a little bit of a departure from this, but until about a month ago, like this strategy is the entirety of all of the modern language models that we've seen do insanely amazing things. And so, I think it's worth spending a second there and asking why actually should we expect this to be a good idea? Why is this what's the intuition for why this should be useful? And I think the idea comes down to two things. The first is that there's a lot of really useful information on the internet. This is one that I have bookmarked because I would go back to this for the last 15 years. How do I save a username and password in Git? And of course, there's about 1 trillion examples just like this across the internet. And indeed, if you have a model that's able to go through every single token on the internet and read a lot of stuff, and what you're training that model to do is to do next word prediction and to model the distribution of that data. If you really want that model to optimize as much as possible fidelity in terms of predicting, store after credential.helper in this case, in order to actually do that really well, it actually has to learn how to reason, and it has to learn it has to learn the facts of that. Actually, yeah, if someone has a question about how to save credentials, this actually is the right answer, and this is just slightly more likely than a wrong answer on the internet. So there's a lot of good reason to believe that this is a good idea. And the other aspect is truly just like a trillion is a really big number. And I think it's easy for us, humans are, I think, bad at understanding scale and order of magnitude, but a trillion is huge. And there's just a lot of capacity to store a ton of information, both in weights, but then also to learn a huge amount about the English language, about humans, and about how we communicate, and about the world through what we write down. Okay, so this is kind of it, right? This is this crazy thing that the world woke up about a year and a half ago and has decided that they need to rub themselves all over with. It's at the end of the day really comes down to just this originally academic toy system that we've just scaled up to an insanely large degree and found can be quite useful. And so having that understanding, going through that history, what does that tell us about the use of language models today and modern language models and the opportunity right now? So to demonstrate this, I just pulled a random abstract by searching PubMed and asked a very simple question of ChatGPT, which is, how many people completed this study? So specifically, I asked this question, I give the study, I give the title, I give the abstract, And if you actually look at this study, it's any human would do this pretty well, but it's not an insanely trivial problem. There's a few different numbers here. There's 316 men who started this study. There's some number here to another 204 number. This is a number that's not eligible. There's a 188 number. These people are also not eligible. There's a 45 number who received the thing. There's 44 who finished the thing. So it's not like the most trivial problem. And I think probably to no one's surprise here, ChatGPT here is able to do this really well. It's able to pull out the truth of the matter. And I guess the reason is because this is like pretty par for the course, right? There's probably somewhere on the internet some test prep type situation where the question is, read this paragraph, SAT test prep, read this paragraph and answer a question about this thing, right? This is a problem that exists somewhere on the internet. Now I can go and ask a much harder problem. So now I'm asking this question, how can temporal lobe reconfiguration be used to improve schizophrenia? And I chat this, and chat can write a great answer. It looks great. It has introduction paragraph. It's got a header. It looks like an article. It has a bunch of information about this. But of course, there's no such thing as temporal lobe reconfiguration. This is something I completely made up. This is just absolutely not at all a thing. And ChatGPT will hallucinate and say this is, will very confidently tell you, here's all the information you need to know about temporal lobe reconfiguration. I would not recommend temporal lobe reconfiguration. And why does this happen? It goes back to everything we talked about, right? Ultimately, this model is just something that's trained to mimic the distribution of internet, to mimic the how text looks on the internet. And yeah, indeed, if someone has written this type of question, the best that it can do is offer a display of something that looks like it would be on the internet, something that looks like a reasonable, good-looking, believable answer that's on the internet. And I think this really gets to the crux of it. So, this is now just the same type of question asked in open evidence. And, what we do that's different from this ultimately is that we leverage these pieces, but we leverage them for individual pieces. I think what this example really tells me is that something like large language models, something like GPT-4 are just insanely valuable and just truly a crazy step function in terms of capabilities for what we can do in the world. But they're not going to be this kind of one and done thing. They're not going to be this thing where we can ask arbitrarily complicated questions and we can ask to essentially solve healthcare, that we can just put over everything, completely throw out everything else and say, solve my problem, just do the thing, end to end, be perfect, right? That's not going to be what these models do, because they're not trained to do that, right? They're really just trained to do next word prediction, and they're trained to mimic humans on the internet. And so what we find, and I'll talk a little bit about, is that the way that we think about these models, and the way that I think we should all think about these models, is they're Lego blocks. They're really insanely powerful Lego blocks. They're Lego blocks that 2 years ago, you'd have to hire a team of 15 people and spend a ton of money and 2 years getting a system that can do what we can, ask Chat or ask GPT-4 or ask other fine-tuned models to do in like 5 seconds. So those are insanely powerful things, but they're not putting us out of a job. And it really is up to all of us when we're talking about how do we make a difference in healthcare to continue building products, to think very carefully about what is the system that we're actually building? What are the needs that we need to meet? And then how do we actually compose these things and put them together in interesting ways to meet these really specific needs that we have? All right, so that's my view on how we got here with large language models. The second half here, I want to talk a bit about what this means for the healthcare industry and what it looks like using these models and building businesses in the healthcare space. So I'll take a step back from the details of the technical side and talk about the motivation for open evidence, kind of as an example case. So open evidence kind of comes from the amalgamation of a few different lenses of challenges and problems. The first is that there's an enormous amount of biomedical information in the world. There's public, PubMed itself is this repository that has 35 million publications. It's a big pile, and the pile is growing every year, and the rate of increase of that pile is growing every year as well. So there's just both a haystack and a fire hose, to double up on metaphors, of information that really is about the kind of sum of our human knowledge about medicine and health. At the same time as there's more and more information, there's also fewer and fewer doctors per patient. I'm sure this is something that you've seen a bunch. There's a well-known doctor shortage that's existing and projected to increase substantially in the next 10 years. And so we have this kind of double whammy of more and more information, more and more specialization, but also less and less capacity per patient to spend time getting at that information and making the best choices. And the result of this, unfortunately, is that medical errors happen, and medical errors are real. And so this is a study published in the BMJ, that medical error is actually the third leading cause of death in the United States. So there are very real consequences for having less than perfect information. Going back to what we were talking about from a technical sense, the way that we address this problem is essentially a constellation of language models, large language models, pre-trained models, third-party models, not machine learning, so constellation of rule-based systems, everything that we put together, leveraging all this technology to essentially find the right references. When it comes down to it, yes, there's a conversational interface, and there's kind of cosmetic similarities to GPT-4 and ChatGPT and systems like that. But ultimately, at the core of open evidence, what we do is we're focused on finding exactly the right references. If you find exactly, the one reference that tells you what the right answer is, or the three references where if you combine them, you get the right answer. Once you find that, that's the hard problem. And after that, that search problem is a hard problem. And after that, layers of fluency are kind of just cherries on the top in a lot of ways. And so what we do at Open Evidence is spend a lot of time essentially solving that problem. And there's a bunch of components that go into that. There's question analysis for analyzing intent. There's ranking different sources, selecting based on questions, different tools. There's source filtering. We rank different sources. We compare evidence across different axes. And it really is just this constellation where each of these components is what 4 years ago would have been an entire 2-year effort and separate team doing these things. We basically just leverage large language models to make each of these steps as easy and efficient as possible. One thing I think that comes up with a lot of these types of questions is the question of how much we can trust and use kind of third-party tools versus training our own models. And this is something that I think we've thought a lot about. We, on our team, are very kind of like machine learning focused, so we have a lot of expertise from the old world of people, very experienced with training models and stuff like that. The truth is that it's a huge mix. There are times when it's really valuable, when you need small models, when you need things to be fast, to train your own models and to fine-tune specific models for our purposes. There are times when it's just super convenient and effective to use the absolute best of the best of the best and call out GPT-4 and all these sort of things. And what we find is that what really matters at the end of the day is not the implementation of any one of these things, but it's about the ultimate problem. And it's about combining these tools and using them in thoughtful ways. And so the result of this, this was kind of our most quantitative aspect, is we looked at the US MLE, which is the kind of med student kind of final exam, licensing exam that happens over the course of a few years. And we use this as our kind of quantitative test, and we're able to show that by leveraging the right information and putting these different processes in place, we're able to pretty substantially improve the state of the art in medical knowledge when it comes down to it. Now, what I think is important, especially in this type of context, is that we talk so much about the technical side, right? And even so far, for the first half hour here, I've talked all about what large language models and what that means and how to use them effectively. But at the end of the day, what that's talking about is the engine, and the engine is critical. The engine has to be there. But what is at least as important when it comes to now we're talking about building a business and making products that actually have impact and find real use is the rest of the car. And there are so many components besides just the engine that are critical, not the least of which is just making a really beautiful car. And I think the most important thing that translates to here in our world is about ease of use and accessibility. And in healthcare, what I've learned is that there's kind of two paths to ease of use and accessibility. And I think they're a little non-obvious from the outset. So the first is the kind of in EHR path, right? So the objective is, how can I put this in the hands of users? How can I give this to people who will use it effectively? And the obvious choice is, okay, well, let's put it where doctors are. Doctors are using EHR systems. These are systems like Epic and Cerner that aggregate information and technology. There's a lot of companies have success doing this. Bridge and Nuance are two examples of, I think, largely speech-to-text systems, and then ecosystems of tools that derive from that sort of stuff. Health Catalyst is an example of analytics. ZocDocs, I think, like scheduling, that sort of thing. And there's lots of good reasons to be in the EHR. But the biggest one, in my opinion, is just ease of use. You're integrated into where all the data is. That's obviously a very clear strategy. But what I think is often very overlooked is it's not the only strategy. And as we'll see, there's a lot of actually good reasons and ways to have real impact being outside the EHR. And this is the approach that I think a lot of there's a number of companies that take this approach and become north of billion-dollar companies, 5, 10, 15 billion-dollar companies in this group here. And this is the path that we go as well. And I think because this is a little less common or less talked about, it's been an interesting experience for us to go through, and I wanted to kind of share how we think about this and what that strategy looks like as a tech company in healthcare. So I was going through my emails a few nights ago. This was top of mind for me because I got this email on October 2nd, which was last week. And it was a response to, it was in the context of a large health organization, in response to an email chain that had started on May 31st, 2023, so almost a year and a half ago. And this is par for the course. This has been our experience, and I think very realistic experience working with large health institutions. There's just a huge amount of red tape, and it's an incredibly slow experience. And that may sound like a triviality, but it's actually a very real problem. As a startup, kind of time is the only thing that you have. And what, as a startup, what you find is that every first idea is bad. Everything you start out trying to do initially is the wrong thing. It's not exactly what people need, and you need to pivot quickly and be able to move quickly. What's challenging about EHR systems and like large health institutions is that while there's a lot of benefits to it, but it forces you to essentially make a bet. It forces you to say, this is what we're doing, and we're going to commit to this thing being really great. And boy, do I really hope that in a year and a half, this is going to be the right thing, and it's going to be what people need and stuff like that. And if you're in that small fraction, that absolutely minuscule fraction that turns out to be right, then you can get lucky and that can work out well. But that's really hard, and there's a large graveyard of companies that make a bet, aren't able to find product market fit, and close up shop because there's nothing there. What's really nice about pursuing strategies outside of the EHR is that you can just make stuff available. You can just put stuff on the internet, and you can just immediately, like within the day, get really important feedback, and you can move and you can iterate and you can improve quickly. Of course, being in the EHR does give you direct access to patient information, so a lot of times that's valuable. Ease of use is important, right? And so anything you can do, putting technology where doctors are, there is value to that. So it's not an obvious decision, but I think this has been one surprising lesson for us, is that it's worth being thoughtful about all the different ways that healthcare and technology exist in the world, and different ways that we can reach users, because that's what we're talking about. But I'll share what this has looked like for us, taking this kind of less trekked path outside the EHR. And essentially what this looked like is we just put open evidence out into the world. And it was pretty bad originally. We started out the Mayo Clinic platform, which was an accelerator program for Mayo Clinic. They tweeted about us. That got us a little bit of traction. We tweeted as well. And we just basically randomly got connected with a handful, like 5 doctors who were excited and could see the vision behind what this thing could be, but knew that it wasn't there yet. And really helped us by telling us, here's like, this is really great. This is really great. There's so many things that are wonderful about this. I see where this is going, but just like do these 5 things because this is what it really has to have happen. And this is really important for a startup because this allowed us to see, hey, there's a real thing here. People will really like this, but allowed us to also iterate really quickly. Since then, kind of what we've done is really just like pull this thread and look at the things that people like and just like be like, okay, let's do that. Just like a ton more, really optimize for those sort of things. And in the process of that, we've now gotten, I think, a huge amount of this type of positive feedback. And it's allowed us to, going this route that's outside the HR, going this route that's very bottom up, has allowed us to just like talk with users and hear what people want and hear what people think and get feedback and follow that trajectory. That's been, I think, really successful for us and really exciting. And at this point, it's even though we're giving up kind of the convenience of the HR, it's allowed us to just have this very organic groundswell and have usage that comes from just putting something that's useful out into the world. And as a result, we've seen this like crazy growth, especially in the last few months, which has been really exciting to see. The other thing that we've been able to do by pursuing the strategy is we've been able to kind of get out of the traditional kind of academic, really well-resourced medical centers and be something that is as broadly applicable as possible. So this is a graph here of the distribution of healthcare professional density of OE users. And so what this means is that for each of our users, or for at least a sampling of them, we take a 20-mile radius around the user and compute the ratio within that 20-mile radius of healthcare professionals to people. And so for each user, that gives us a sense of what's the context in which that provider's using open evidence. Are they using that open evidence, in a setting where they're just jam-packed next to a bunch of doctors, for example, in Mayo Clinic in Rochester, or are they in a rural community where they have very little access to other providers and other specialists and try to serve a large population? This graph is that distribution. And so we can see, for example, we have a big spike here in the Rochester, which is where the Mayo Clinic is. That's where we came from. We have a spike at Boston as well, probably because that's where we're situated. And there's also obviously a really strong medical presence in Boston. You get into LA, San Francisco. These are still really well-resourced areas and very high on the list of kind of academic places. But what you notice is that we have actually the large majority of our usage at institutions and health settings that are less resourced than these large cities, that are settings that don't need to have bought into, for example, the Epics of the world or the Cerners of the world, and being those large health systems. They can be private practices, they can be smaller communities, they can be more rural areas and stuff like that. And so this is, I think, something that's turned into something that I think has been really motivating for all of us, and just another benefit of being outside of the HR and being able to not just be so closely tied to only the most kind of prestigious elite type of use cases. Okay, and this has been now one of my most favorite things that I've seen, which is that taken to the extreme, the kind of most largest version of this kind of thing is about being able to go beyond just the US and being able to go beyond kind of traditional health settings. And so actually what we saw in the last month especially is a huge spike in usage from Latin America. Mexico and Brazil are two of the biggest ones. And it's been spiked a lot by people who are just people who are just talking about open evidence. And I hope that this can come through, the audio can come through. I'm worried it's not gonna. Okay. Let me see. Okay, I have a feeling this is not going to come through, but the people in the room will be able to hear. So this is just some random TikTok that we found on the web. We did not at all pay this guy to do anything or like talk with him at all. I actually have no idea what he's saying, so I don't speak Spanish. But he and a few other people just started making TikToks about this. Again, just because it's available on the internet for healthcare professionals who want to use it. And so this has led to this explosion in usage in Mexico, especially, and Brazil secondarily. And yeah, it's really just been crazy to see.
Pero un momento, lo mejor de todo, no solamente te da la
these just
respuesta,
truly random people talking about it and making it their own and using it in ways that we never anticipated, including, for example, like
pero lo
generating
mejor de hecho es
answers
que te
in
pone la
in Spanish.
referencia bibliográfica, lo que nos gusta a nosotros como médicos.
Okay, so that was a fun thing that we saw that I wanted to share. All right, so my point with all this is one of my biggest learnings from pursuing this from the healthcare point of view is that there is a lot of value to really just lowering barriers to entry, just putting things out into the world. And if you really are able to make tools that are useful, there's a lot of opportunity for kind of groundswell, bottom up type growth that you can't get by following very kind of traditional big tech healthcare type situations. Okay, so we've talked about language models. We talked about where they came from, kind of what they're actually doing, how they're trained. Then we talked about a little bit about open evidence, what goes in under the hood to make a lot of these different processes work, and kind of the business and strategic side of what does it mean to make a startup in this space in healthcare. And what I wanted to do is just take a second and talk about where are we going? What do we take from these different components? What's the lessons that we can take from at least my experience with open evidence, and what does it look like for AI in healthcare a little more broadly? So this is the next few slides are taken from Travis Zach's AI citizenry for healthcare professionals like mini course, which he's graciously shared with me. Travis is an advisor for us at UCSF. So we gave this example of this patient who presents with chest pain, and we're going to walk through the steps of what this process looks like for this patient. So it starts, our patient develops crushing chest pain working from home. At each of these stages, actually the details are not so important, but at each of these stages, what we're going to talk about is that each of these stages is characterized by some amount of inputs, and then leveraging those inputs, making decisions on the basis of those inputs, and then taking actions on the basis of those decisions. And so, for example, they start off, they develop crushing chest pain. They might have symptoms, they might have a sensor. They perform some decision-making process. They go to Google. Hopefully, at some point they'll go to open evidence, and then they take some action. Maybe they call 911, something like that. And then I'm not going to walk through this for every single one of these steps because I don't want to belabor this too much. But we can walk through what the sequence of events that happens are. So now our patient arrives at the ED triage station. There's more inputs. Now there's decisions that are being made by nurses. Now they're roomed in the emergency department and they're seen by the care team. Now there's a blow up in types of inputs. There's physical exams, there's labs, there's images. There's more decisions. Now the decisions are being made by a physician or by a specific care team. There's outputs. Maybe there's choices to go get more labs. And so now there's a recurring process here. But we can, keep walking through this. There's now a procedure. During that procedure, there's inputs. We learn something. The procedure happens. There's data about the procedure. There's operations throughout this entire process. There's optimizations around how are we triaging patients in the emergency room? How are we monitoring care? How are nurse shifts laid out? The patient eventually goes home. They're still interacting with the patient team, with the primary care team. Maybe they're talking through MyChart to their providers. Maybe their provider is writing clinical notes. Then there's this whole parallel track that's happening at the insurance company in terms of billing codes, diagnostic codes, leveraging that information in a cyclic way, building that into their internal data processes. And then, especially for regulated spaces like healthcare, these experiences and this data goes into public data sets and public research initiatives. And so, what really struck me looking at these slides and the reason why I wanted to go through this is that healthcare is an incredibly complicated process. It has been a complicated process for probably 10,000 years since there's been anything that we've called healthcare, and there's there's a lot of components, right? Open evidence, I think, addresses a small fraction of component parts of these things that are in here, but there's a huge open space of areas where there are inputs and we're making decisions based on those inputs, and we're trying to do the best possible job to make the best possible decisions and to ultimately give the best possible care as well as good as possible. What I see for this age that we're in now with large language models and with AI is that we have these building blocks. We have these tools that are just insanely powerful, that are more powerful than probably any building blocks we've ever had. And with the capacity to leverage these building blocks without having to, build teams of 15, 20 people and pay them over the course of 2 years to develop some of these different things. So we have, I think, more capacity than ever to go into this incredibly complicated process and bite off chunks and take components that traditionally have been very hard and try to make them more efficient, try to make them safer, try to improve care across the board. Ultimately there's a huge set of important things, and now we have the capacity to do those things. And so, I'll finish here on a note about trying to learn what we can from history and from what I think is the closest analog to where we are in terms of this capacity right now. And I think that analog is from the dot-com boom and the dot-com burst. So this was now before my time, but I really think the closest analog is the dot-com boom, which is when there was just this complete blow up and an enormous amount of hype and excitement around what the internet can provide. That really was the last time when there was such a fundamental capability shift and shuffle, really, when it comes down to new technology, new capabilities entering the world, and an uncertainty of what does that mean. There is no shortage, as there is today, about discussion about how this is going to cure cancer and save the world and blah blah and do all these sort of things. And ultimately, there was a bubble, and that bubble burst. Right, there was hype, and this is that period. This is the Nasdaq index. There were a lot of companies that died. But we fast forward now 25 years later, and what's really striking to me is that every single one of the top 5 largest companies in the world are companies that either started during that time period or were companies that leveraged the internet, and that all of those things that were definitely overhyped, that they were able to find these nuggets, these things where there actually was really extreme value. And again, there's a large graveyard here, right? There's a large graveyard of companies that didn't succeed and weren't able to find this value. But what I think characterizes this set of companies that now literally rule the world are these companies were able to get at the reality of it. These companies were able to understand at the time of the internet that shipping was going to be important, that physical devices were going to be important, that GPUs were going to be important. And I think those are not easy inferences. It's easy in retrospect, obviously, but at the time, those aren't easy inferences to make. But I think for us, this characterizes the challenge for all of us, right? At this time when there's an insane amount of hype, how do we cut through that? And how do we find what those nuggets are? But the positive side is what we can see from this is that for those small number of winners, for those small number of people who are able to really identify and be right and make big bets about what those nuggets are that have real value, and for those people who are able to leverage that value successfully, there truly is a huge upside and really enormous value that's able to be created. And I think this is the moment that I see that we're in now with AI. What I can almost guarantee is that in 15, 20 years, the companies that are going to be the biggest companies in the world are going to be the companies that leverage AI properly, that take this moment of shuffle and switch up and uncertainty and new capabilities, and are really thoughtful about what is the reality of them. How do I actually use these in the best way possible, in the way that they're best designed for? And how do we make something really great? And so I'll end with this quote that I really like from Fred Wilson, who was VC in the dot-com era. And what he said was, a friend of mine had a great line. He says, "Nothing important has ever been built without irrational exuberance," meaning you need some of this mania to cause investors to open up their pocketbooks and finance the building of railroads or automobiles or aerospace industry or whatever. and much of the capital was lost, but also much was invested in high throughput backbone for the internet and software and databases and servers and all that stuff. And very practically, I think nobody would question that, every iPhones, computers, the internet, all of this completely defines our life today. And so, that's I think the message of the moment right now. Like, yes, this is a absolutely insane moment. Yes, there is irrational exuberance. I think when we're at the point where the physics Nobel Prize is going to a computer scientist, I think it's fair to say there's at least a bit of irrational exuberance. But there's also a really, really just insane amount of capabilities that are unlocked right now. And I think this is that moment that is in a lot of ways really like a once in a career moment. And that's why I'm doing this. That's why I've effectively kind of dropped out of my PhD to seize this moment. And it's a really exciting time, and I'd encourage all of you to really seize it and make the best of it, and find the reality beyond all of this noise and make really great things. So that's what I got. Thank you.
Thank you. So we take questions from the room, and then I'll read the questions in the Q&A section. But I can start with a question about the kind of queries that clinicians would be using open evidence for. Like, do they tend to be more contextualized to a specific patient? Like, is it a question about the care that you're engaging in at the moment, or do they tend to be like more general questions? Because that will also help me understand the choice of going out of HR.
Yeah, it's a great question. So the truth is it's a mix. So there's two axes that I see. So one is in EHR and out of EHR, but there's another axis which is like HIPAA compliant versus not HIPAA compliant. So it's totally kosher to take a note, put it in a HIPAA compliant system, even if that's out of the EHR. It's kind of just a loss of convenience. But what I think is has been interesting is that we actually don't need a huge amount of patient context. There's a lot of value not in having every lab value that a patient has ever been scheduled for and taken, and all of those outputs, and 10 years of clinical notes or whatever. Often there's what's helpful is just a kind of summary. So like, this patient has so-and-so whatever diabetes with like one biomarker or something like that. And I think that's the most common thing that we see is a light amount of patient contextualization. That's kind of the minimum that's required. And I think that's a good happy medium between providing information, but not just being onerous, essentially. Yeah.
And
so because it's free and open to everyone, I was just wondering, how do you plan to be reimbursed or sustain that in the long run?
Yeah. So for us, and actually I think this is shared with a lot of the tools that are outside the EHR, but it'll be an ad-based model. And so that'll be a way of making it free, making sure that people, no matter where they are in the United States, can always use it. And what's important for us in the specifics of what we do is just keeping it very separate. So there'll be ads, they're very clearly delineated. They don't affect answers. They don't affect where the information comes from, and that's but yeah, that'll be the monetization model.
I'm curious about the international growth that you talked about.
Yeah.
So currently the tool is only in English, I'm assuming?
So I mean, that's one of the great things about large language models is that fluency layer is not specific to English. So we built in a bit of specific stuff to be able to handle different languages well, because what is in English always are the data that we draw from. So all the references are in English. So we put a bit of thought into what happens if someone puts a Spanish query in, can they get the right references? So there's a little bit of thought there. But we get a lot, it's a great example of, I think, something we get kind of for free for OpenAI spending whatever billions of dollars and hiring all these people. We kind of very much get a lot of value being on the backs of those giants. Yeah.
What's your perspective on the different models, so GPT-3, 4, and O1? It sounds like you have fine-tuned GPT-3. You've mentioned that works quite well. Then for models like 4.0, where they've done a lot of fine-tuning on their own user preferences, does that actually conflate your model more? I mean, then with O1, further improvements.
Yeah,
I see that working.
that's a good question. So I think there's kind of two classes of things which are little bit separate. So one is like, what is the base model that's being used for any of these types of things? And that's, you know, that's the same for GPT-3 or GPT-4. It's also the same for like open source models like Llama, for example. When we fine tune models, we actually start with Llama just because it's easier. We get to do it ourselves. It's open source. What the biggest difference where OpenAI and these other services like Anthropic as well input their opinions really is in the kind of chat side. So what they do is that they make base models available, and it's really the same thing for Llama. So Llama also makes those base models available. Then internally, OpenAI will take, for example, 4o, that model, and they'll train it further and do prompt tuning to make what is ChatGPT. So that's really where they encode a lot of their biases and their peculiarities and stuff like that. But the kind of more raw models, these base models, don't really have these types of things. And so, but whether it's prompt tuning, so putting information in the prompt, or fine tuning, so like actually changing the weights to have whatever biases we need, those are two approaches that we take. But yeah, we're never using what kind of the public sees as OpenAI or whatever as chat, because that has a lot of their biases included in it.
Speaking of biases, a lot of medical research, especially foundational research, does have a lot of bias,
Yeah.
especially racial, gender, economic disparity biases. Or certain conditions are understudied or aren't studied at all in certain groups. When you're creating this model, were these like any considerations that you took into account, or like in use cases have physicians talked about like for particular populations, maybe the results aren't as like robust or aren't as like reliable?
Yeah, no, it's absolutely true. So the approach that we take, as much as possible, is kind of stand on the shoulders of peer review, and that does have some problems, right? There's bias in the peer reviewed literature, but what I think, you know, what I see, and one of my biggest learnings, kind of technically about how literature and the publication process works, is that there's 30-40 million publications in PubMed, and what's pretty remarkable is that there's almost a publication for almost everything that you can imagine. I mean, not like a phase 3 clinical trial necessarily, but there's a lot of work in a lot of different spaces on almost everything. And so I think what we find is that, especially if users are specifying details of, you know, race or whatever, the benefit of what we can do actually is we can find those smaller, less well-known type studies. We can find the information that is focused, even if it's not published in New England Journal of Medicine, is focused on either subgroups or subgroups and stuff like that. And you know, I think it's always important to talk about in this type of situation, like what your comparator is, right? What we find is that when the comparator is doctors, and you know, let's say your 63-year-old doctor who's been seeing patients for 30 years and is you know 20 years removed, 30 years removed from all of the training that goes into being a doctor. Compared to that, actually having access to the entire literature allows us to be a lot less biased and a lot less focused on, well, you know, once 10 years ago, I saw a patient and this thing happened to that person, so now I'm going to treat all these patients in that sort of way, with that sort of thing. So I guess my answer overall is it's definitely an imperfect system. But I think that actually moving away from humans being the deciders for what's the information that gets surfaced into a system that can access the millions and millions and millions of things that people just talk about and study about, gives us actually a lot more flexibility to find the right study for the right person.
Could you talk about the liability framework of this?
Yeah, so you know, ultimately we're not really so we're not making decisions for doctors. And I think what this comes down to is, you know, one thing that we've thought a lot about, which is, should we make this available to patients? Should we keep this, you know, only available for doctors? Yeah, what's the context in which people are using this? And one of the biggest reasons for making it available to physicians is that there's there's a lot of value in being able to access the right information, even if you're not right, like literally 100% of the time. So the analog that I know for this is like ChatGPT and Copilot for programming. Copilot and ChatGPT have like very realistically, maybe probably like 4 to 5 times as effective a programmer. It's probably right like 30% of the time, like fully right in terms of me not having to make stuff. And so for me, what that tells me is that all of these tools ultimately are not about like they're not a set and forget it type thing. They're not just like, okay, put in exactly blah blah blah. I'm gonna close my eyes, I'm gonna close my ears, and I'm just gonna do whatever it says with no thinking. The value is in having something that can surface information and find good sources and find good references and support a conversation. And so when that's used in the hands of physicians, in the hands of trained experts, I think that's really valuable. And then, you know, it's like a Google search, right? Like there's a lot of information you can get from Google. Google doesn't become liable for you know, decisions you make. That's kind of still on you as a physician, but hopefully we can give you the best information possible to help make that decision as well as possible. Yeah.
Have you thought about expanding this to like assist researchers do like literature searches and stuff like that?
Yeah, it's a great question.
And maybe I can just look in the, because there are two
Yeah,
questions
related.
online that are related, which is
Yeah,
who's your envisioned user? Like what if a patient uses this? Do you factor this into your filtering processes, or do you just envision one type of user? Like what other
Yeah.
users a researcher would the query be different?
Yeah, right. That makes a lot of sense. So one choice that we've made more from a product point of view than a kind of technical capability view is really to make this a walled garden, to make this something that you have to have an MPI or you have to otherwise be a healthcare professional to access. And there's a lot of value in doing that because we get to make a product that is really focused on what physicians need. And what we see from users is that there's, I think, a huge amount of interest in having things that are made from the ground up for physicians. And all the decisions end up being at the edges in terms of what questions do we allow or not allow? What do we assume about the literacy and the kind of way that doctors, the reading, you know, comprehension level and use of jargon and knowledge and these sort of things. One thing that we've heard from users, for example, is thank you for not making it too legalese, right? Thank you for not saying at the end of every answer, like, but it's important to consult a physician, or it's important to, you know, more study is needed for these sort of things, right? Like, yeah, okay, obviously, like we get it, we're physicians, right? And so I get if you I think if you get to pick a specific audience, you get to make choices that make a really great product for that audience. And yeah, so that ends up really being our focus. I think on the patient side, you know, I think that's something that we're definitely thinking about. But actually, the biggest reason not to, in some ways, is we really want to make an experience for physicians. We don't want to, like, you know, what I always say is we're not here to replace physicians.
Yeah.
I think that's the really important thing. We're not here to disintermediate physicians and have something where you can have like an AI doctor that patients
Yeah.
can go to instead.
I think the difference is that the nature of access to a tool like this, because it's just public.
Yeah.
And like patients will instinctively like just like they Google symptoms in Google, or like any other search engine. There's no barrier for them using this tool as well.
Yeah, well, so for this, basically the way this works is you get like a question a week, basically. So you can go and you can try it out, but very quickly you get kept and you get blocked.
Okay.
And then you have to sign up and put in your information. But the analogy, you know, the reason to do that sort of thing, and this is a lot of our motivation, is the alternative is patients then go to Google, right? And like you say, there's no way that's better than getting information from open evidence, right? So that's what we try to trade off. And I don't think we know exactly the right answer yet. I'd love to eventually be able to serve patients and give them better experience than Google. Yeah.
Any other questions? Okay, so let's thank our speaker again. Thanks everyone who joined online. See you next week.